Dear students, today's topic is very much related to the previous lecture. As you remember or you recall it, the previous lecture is velocity analysis by relative velocity method. So the today topic of discussion is velocity analysis by instantaneous center method. So we are dealing with the velocity analysis by somewhat a different technique. However, I will request you to please go through the previous lecture because the concept discussed in the to be discussed in the present lectures are somewhat related to the previous lectures as well. So if you gone through or you studied the previous lecture, then the present lecture will not be much difficult for you. As the today topic of discussion is velocity analysis by instantaneous center method, so it's worthwhile at first to discuss what's mean by this instantaneous center. So to define the instantaneous center, or we also call it IC, um, I will request you to please recall your memory about the mechanism. So mechanism is made up of links and joints. So most of the links in the mechanism, they are in motion. So if I request you to please um, pick any of the link which is in motion and focus on it, just as you can see I mentioned a example of a link at bottom left hand side of this slide. So there's a link with the title link in motion. So just imagine that there's a link which is in motion. So when this link is in motion, so what is happening that this link is moving, but it's also rotating around some imaginary point. I will repeat again. If this link is in motion, so with motion, this link is also rotating around some imaginary point, and this imaginary point around which it's rotating, we call it instantaneous center. So to clarify the point, I will run a simulation, or you can say the animation, whatever you like it. So by running the animation with the verbal narrative, I will try to explain my point, that what means by that link is moving, but it's also rotating. So it's rotating around instantaneous center. So please focus on this left hand side, the bottom left hand side, where you can see a link. So what will happen that at let's see that any particular instant means that you have a stopwatch in your hand and you are watching the motion of the link. So the, as you know, the stopwatch clicks like second 1, second 2, second 3, second 4, second 5, second 6, and so on. So you are watching a link which is in motion, and also simultaneously you are observing your stopwatch too. So at second number 1, first second, what's happening? The link is in motion. So you are seeing that the link is in motion, but it's also rotating around some imaginary point. So this imaginary point around which it's rotating is called instantaneous center at this particular instant or its particular time. So time 1 second, this link is in motion but also rotating around this instantaneous center. What will happen in second number 2? Tack. Yeah, the link is in motion, and in particular and then in second number 3, the link moves its position, and also the instantaneous center, the position of instantaneous center, it's also changed. So what's happened that it at second number 1 the link was here and the instantaneous center is there. As the link moves from position this to there, the 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 the, the instantaneous center location is also changing, because the link is in motion from position 1 to 2 and then 2 to 3. Also it's rotating around some imaginary axis which is called instantaneous center. So at first the link was here in time 1 second and it's rotating around this point, the first IC. At time 2 second the link is here now, the link has changed its position from this to that. However, it's also rotating around some imaginary point, the instantaneous center. At time 3 second, because clock is clicking, so at 3 second link position is here, but it's also rotating around a IC which is IC number 3. So at time 4 second what is happening? Yeah, the link has changed its position, but it's also rotating around a imaginary point. So the position of imaginary point around which the link is rotating at this particular instant, a particular time, this particular time is time 4th second. So at time 4th second the position of link is changed, but also this link is rotating around a imaginary axis which is called the instantaneous center. The position of instantaneous center is also changing because the link is in motion. The link is in motion means link at time 1 second is here, link at time 2 seconds is here, link at time 3 seconds is here, link time 4 seconds is here. At every instant, at every second the link is changing its position, but also as you can see this link is changing its position, but it's also rotating around some instantaneous center at this particular time. So at time 1 the instantaneous center was here, at time 2 second the instantaneous center moves here, at time 3 second it's moves here, and time 4 second it's moved here, because this instantaneous center is changing its position with respect to link, because this link is in motion and also it's rotating around this instantaneous center. If we combine or make a path of these instantaneous centers just like this, so time 1 second, time 2 second, time 3 second, time 4 second, and so on. So if we combine these these instantaneous centers, then there will be a path of instantaneous centers around which at specific time the link is rotating around. So this path is called centroid. So I will repeat again for the very last time to clarify the concept of instantaneous center and this centroid. So let's imagine the link is at position 1 at time 1 second. So this link is rotating around some imaginary point which is called instantaneous center, and this is instantaneous center at time 1 second. So at time 2 second the link has changed its position from here to here. Also this link has changed its position, but its axis of rotation is changed as well. So this IC number 2 is changed as well. Similarly at time 3 second the position of link is changed, but the location of IC around which this link is rotating as well is changed. So at time 4 second the position of this link is changed, and with respect to this position of the link, because this link is changing its position, but it's also rotating around some imaginary axis, the IC number 4, around which this link at time 4 second is rotating. So the position of these ICs, IC1, IC2, IC3, IC4, it's also changing with respect to time. And if we draw a path of so we draw a path from time 1 second, 2 second, 3 second, 4 second, just as here, time 1 second, 2 second, 3 second, 4 second, 5 second, 7, and so on. So the path of these instantaneous center at any particular time is named as centroid. A very important characteristic of instantaneous center is that although the link is in motion, so when link is in motion, so a link will have certain velocity, or any point on the link has some velocity, but the velocity of instantaneous center at any particular time will be 0. This means that although link is in motion, so whenever link is in motion, it means that it will have certain velocity, but at any particular instant the link is rotating around a imaginary axis which is called instantaneous center. So this link has a motion, it has a velocity, but in essence the velocity of instantaneous center will be equal to 0. Means there will be a no velocity concept for instantaneous center. Although link is moving, it will have certain velocity, but the velocity of instantaneous center at any particular time for any particular position of the link will be equal to 0. So I will repeat it again. Whenever the link is in motion, definitely it will have certain velocity, but at any particular time, just as time 1 second, 2 second, 3 second, 4 second, and so on. So any particular time, for example time 2 second, when the link has changed its position from time 1 second to time 2 second, definitely it will have certain velocity, but at time 2 second when the link has changed its position, but it's also rotating around its imaginary axis, the instantaneous center. So at that moment, at time 2 second, the velocity of this instantaneous center will be equal to 0. Although there will be certain velocity for the link, but the velocity of instantaneous center will be always equal to 0. So please remember this concept. Although the concept of instantaneous center is very much clear to us, however, we are very much interested to know the exact point of instantaneous center for any link at a particular time, for example at time 1 second. In the previous slides, I show you an animation where I draw a instantaneous center around which the link is rotating at the particular instant, for example time 1 second. If the position of link is changed from one position to another position at from time 1 second to time 2 second, although the position of link is changed, but also the rotation axis around which this link is rotating at time 2 second is also changed. The instantaneous center is also changed. So in the animation I just draw a instantaneous center as a arbitrary point. Arbitrary point means that it was a false point. Now in this slide we will find the instantaneous center for a link at a particular time, for example time 1 second, with 100% accuracy. So to pinpoint the instantaneous center at any particular time, for example time 1 second, what we need? Definitely a link. So this link is you have saw this link um, um, so many times in the previous lecture as well. So a link with 2 points A and B, if this link is in motion, definitely the point A and B, they will have a certain velocities. So point A has a velocity VA, the green color, so the direction of velocity and the magnitude of velocity. So as you know that velocity is a vector quantity, so to define a velocity we need two things, the magnitude and direction. So at point A, the direction of velocity is this one, the green direction like this, and the magnitude of velocity will be from here to here. So from the base of the arrow of this green color arrow to the tip of this green color arrow, it represents the magnitude of velocity and the direction, as you can see here. Similarly, as point B is in motion, so what is happening that this red color vector, the VB, it represents the direction. So direction of VB is here, whereas the magnitude of velocity will be, this VB is can be counted from the base till to the tip of this arrow. It represents the magnitude. So magnitude and this direction of velocity will give us the total concept of VB. So to define VB, we need two things, the magnitude from base till tip of this arrow and the direction, which is here. And to find the instantaneous center at this particular time 1 second, what we have to do, we have to draw a perpendicular to VB, and we have to draw a perpendicular to VA. Let's see, if we draw a perpendicular to VB and VA, what we will get? A intersection. So both these perpendiculars, they will intersect at a point, this IC. So this IC is instantaneous center. So by drawing a perpendicular to both the velocity vectors, what we will get? A intersection of these perpendiculars, and these perpendiculars, when they intersect, they form IC. So this symbol you can see, it represents the 90 degree of perpendicularity. 90 degree of perpendicularity. So the intersection of both the perpendicular at a certain point, they will give you IC at that particular time. For example, time 1 second, the IC is here. Time 2 second, definitely, because the link is moving, the IC position will also change. Now we are interested to derive the relationship between the velocities like VA and VB. For this derivation, we have to recall our memory. If you recalling your memory, then I hope you have already observed this triangle, which is just shown to you at the bottom right hand side. So this is a velocity vector where at the center O there is a velocity VA, the green color, which is similar to this one, and VB, which is similar to this one. And then if we draw an arrow from tip of VA to tip of VB, what we will get? Relative velocity of B, point B with respect to point A. So this triangle at the bottom right hand side is from the previous lecture, and this link with the velocities and this instantaneous center is from the present lecture. Now to derive the relationship between velocity, what we are doing, we are doing some interesting things. Let's see. So what we will be doing, we will move this bottom triangle in such a way you can see that, yeah. So if we rotate this triangle, and by rotating, and then also we are squeezing this triangle, then you will observe that this triangle, which is moved from here to here, like this way, and also it's squeezed, then a very interesting observation you will be seeing that this triangle is similar to this triangle. Even the lengths, like this length, so this length is similar to this length, this length is nearly similar to this length, point B to C, and also this dotted length is very much similar to this length. So in brief, triangle CAB is very much similar to triangle O small a small b. So both the triangles are very much similar to each other. So what we are doing some mathematical formulation. So we know that velocity at point B, VB, velocity at point A, VA, the green color, is equal to angular velocity into distance, perpendicular distance CA. So CA into the angular velocity, the angular velocity, the rotation of this link. So VA is equal to omega, the angular velocity, into the distance CA. If we take this omega to the left hand side and the remaining components to the right hand side, so we will have the relationship omega, the angular velocity, is equal to VA by CA. Similarly, VB, the velocity at point B, is equal to angular velocity multiplied by CB. So again we are doing the same thing that we have done for the VA, that we taking the omega to the left hand side and the remaining components to the right hand side. So omega is equal to VB by CB. So omega in both equations are common. So omega is equal to VA divided by CA is equal to VB by CB. The very interesting thing, as I already mentioned you, that the from this triangle, that this velocity has two components. One is the magnitude, other is the direction. So if you define the velocity, then you need two things. The first thing is the direction, and the second thing is the magnitude. So this VA is same as this VA, so there is no difference. So the magnitude is defined by velocity of VA is O to A. So the magnitude from the position this distance from this to this point, from O to A, will give a magnitude, and the direction of velocity is in this way. So if we replace the VA with its magnitude OA, and similarly VB, which is here, the magnitude of velocity VB is from O to B, OB. So if we replace the magnitude of VB to OB, then we will have we can rewrite the equation for the omega is omega is equal to OA divided by CA is equal to OB by CB. So this is just a simple mathematical formulation to get something about a relationship between the velocities. In the previous slides, we only focused on a single link with its instantaneous center at a particular time, but now we are dealing with the mechanism. So in case of mechanism is composed of links, which are many, and the joints. So if links are in the motion, then each link will have its own instantaneous center at a particular time or instant, for example time 1 second. So if there are 6 links, then each link, if it's in motion, then it's also rotating around its own axis, so it will have its own instantaneous center. So link 1 will have its own instantaneous center, link 2 will have its own instantaneous center, link 3 will have its own instantaneous center, and similarly goes for link 6. So at time 1 second we will have 6 instantaneous centers for 6 links. For the case of ease, if we are interested to find the number of instantaneous center for whole mechanism, then we have a very simple formula where the capital N represents the number of instantaneous centers, whereas the small n, it represents the number of links in the mechanism. So you have to count first the number of links in the mechanism, and we are interested to find the number of instantaneous center for a whole mechanism. So we have this formula: capital N, the number of instantaneous center, will be equal to small n, which is the number of links, multiplied by number of links minus 1, bracket close, divided by whole 2. So by this formula we can know the number of instantaneous centers for a whole mechanism at any particular time. So that's all for today's lecture. If you have any question or query, or you didn't understand any of the concept, then please let me know via Google Classroom or WhatsApp group. Then I will try to answer your queries at the earliest. Thank you.